I'm delighted to have a chance to talk to you about the value of tacit knowledge in both minds and machines. And for our English-speaking audience, a few words about myself. I have an academic background primarily in economics and the decision sciences. And for many years, I spent time at Royal Dutch Shell. And while at Shell, I was a chief information officer and also vice president of information technology globally. And that included responsibilities for knowledge management. After Shell, I founded a company called Many Worlds, and we're focused on two things. The first area is advisory services in the intersection of strategy and technology and decision science. The other big area for us has been AI and machine learning, which we got into very early, a couple decades ago, before everyone was talking about AI, primarily around recommender systems. Developing those, things like expertise discovery and so forth, but also branched out into other areas of machine learning and created some foundational aspects that are used today in things like generative AI and so forth. And along the way, I wrote a couple books, one of the first of which was oriented to AI and machine learning more. The second one, which is shown here, Optimizing Data to Learning to Action, is oriented more to general business performance and applying various techniques related to machine learning, for example, knowledge management, and so forth. And a lot of what I'm going to talk about in this webinar is based on the concepts in the book, although there's some other ideas sprinkled on top as well. Now, the words in the title of this webinar are important. For example, the word value. You know, that's a word we use all the time in business presentations. It's kind of a throwdown word, commonly used. But here we're going to take it very seriously. We're going to look at it from a first principles standpoint, and it's going to guide everything that we talk about in this webinar. Another term you'll see is tacit knowledge. Most of the folks in this audience will be familiar with tacit knowledge, but primarily with regard to people, humans, right? I mean, what else could it apply to? But more recently, it's come to apply, surprisingly perhaps, to also our computer systems, our machines. And that's going to have, and already is having, a significant impact on value. And so we're going to bring those together because it's key for people in the knowledge management space and also like learning and development and so forth to be aware of the opportunities that we now have that we really didn't have even just a few years ago. Okay, so if we're going to take knowledge value seriously, where do we start? Well, we have to start with decisions. And that's because all value ultimately derives from our decisions. Our cumulative decisions, big and small, ultimately drive all value in our organizations, right? Certainly there can be good and bad luck, and therefore, you know, the effectiveness of our decisions doesn't correlate perfectly with, for example, our financial results, but it's pretty close, right? Because luck tends to even out over time. So it's kind of a truism, if you think about it, that every drop of value ultimately that our organizations create has to come from decisions. But it's often forgotten or overlooked in sort of the heat of the battle of our everyday business lives, right? We don't think about it all the time. But again, if we're going to take value seriously, we've got to. And everything else we're going to talk about, whether it's learning, whether it's knowledge management, whether it's technology, that's all a means to an end. And that end is more effective decisions because we want to drive value. Okay, so if we want to have more effective decisions, how do we do that? Well, we have to look at the context in which decisions are made. And that context is always within what I call a data to learning to action, or DLA for short, process, right? And these are universal processes. I mean, anything with neurons does one of these processes, including us and our organizations when we're making decisions. And increasingly, our machines, using machine learning techniques, do this process as well. At a very high level, we can represent it by this simple diagram, which just shows data entering the process. There's learning from the data. The learning informs a decision, and then an action occurs. Sometimes, not always, but sometimes the action will generate additional data that feeds back into the process. So this is a universal process, right? Any animal, including us, does this process. It's just fundamental to our lives. And again, increasingly with machine learning, this process is occurring within our computer systems. But what we're most interested in is driving value in our organizations. And for that purpose, we can expand out that simple diagram into a few more elements as shown here. And these elements are pretty self-explanatory, so I will just touch on them very briefly. It again starts with data, but now the data is filtered or conditioned in various ways. And then that filtered data becomes information, or we could call it maybe knowledge at this step. You'll see in the next slide, it's fuzzy where knowledge is, and the word knowledge is a little fuzzy. So we'll get to that, but let's just call it information at this step. And then that information is perhaps explicitly searched for, or it might be surfaced automatically, which we can call discovery. Either way, that information that's accessed is used to make predictions about the world, right? And those predictions may be processed in different ways. Maybe that predictive information is displayed on digital dashboards. And often there's a collaboration step, right? Multiple people collaborating on making the final decision, and then an action occurs. Now, in that simple diagram on the last slide, I had an element called learning. Where did that disappear to? Well, it's designated by the arrows on this diagram. And that's because learning flows along a DLA process. And as it flows, it generates knowledge. And then the knowledge informs a decision. So there's a distinction here that's always important to keep in mind. Learning is a process, a temporal process. There's a change over time. Whereas data or information or even knowledge, we could, in theory at least, measure it at a point in time. It exists at a point in time. So again, important distinction. Learning is a flow. It's essentially a process itself, embodied within the DLA process, right? And knowledge and information, data, sort of what we call a stock, exists at a point in time. Now, this diagram can apply to about any decision that you can possibly think of in an organization, right? It's quite universal, quite adaptable. I call it sort of a canonical diagram that we can use over and over again, and we're going to keep coming back to it in this webinar. But it's really, again, more universal than that. It applies to organizations, but if a moment's reflection, I think, will convince you it's also what goes on in our own heads when we make a decision, right? Because we have a massive amount of data coming in from our sensory organs all the time, every minute. And we have to dramatically filter it down to that which we are attending to in any given moment. And some of it we might store in short-term memory, even less in long-term memory. Either way, we might explicitly recall it, or sometimes it just pops into our head, right, from our subconscious. Either way, again, we make predictions about the world. Ultimately, the brain is a predictive machine. That's what we're doing all the time, predicting, seeing if our predictions are right, learning from the predictions. Even the collaboration step fits, because in our brains, there's multiple modules that both compete and cooperate at the same time to make a final decision. So again, this is universal, has to be applied to every decision that we want to really improve, or at least important decisions in our organization, to drive value, right? Now, as I mentioned, knowledge, though, where does it reside on this diagram, right? Is it at that information management element, or is it after we retrieve that and start to do some modeling with it? Or is it the output of the models that we might display for decision makers? Or is it in the decision makers' heads when they're basically collaborating and adding additional insights of their own in making the final decision? It's not clear, right? It's not clear. Knowledge in general, like a lot of terms, somewhat fuzzy, and therefore knowledge management, managing knowledge, where does the scope begin and end? And again, not clear at all. And my recommendation, therefore, is, DLA processes are universal. They always apply. They've got a little more detail, and therefore they can be good communication aids when people are talking about things like knowledge, when people are talking about learning, when people are talking about knowledge management, who should be doing what's important to improve, and so forth. It can give you a little more crispness in your communications so that, again, you can make the processes more effective, which drives value. Okay, so we're going to come back to this DLA process because it is the key to value, and that's what this webinar is all about. But let's take a minute to consider the way humans make decisions a little more carefully. And the best source that I know of for that is a book by the Nobel Prize-winning psychologist Daniel Kahneman called Thinking Fast and Slow, which is based on real science, right? You sometimes see, pop psychology sort of things that really don't replicate when people try to replicate the scientific study, et cetera. This is based on real science. It predates Kahneman. Kahneman just popularized it in his very well-selling book of over a decade ago here. And the point Kahneman makes is that we have two modes, basically, of decision-making, two different cognitive modes. The first he calls system one, and this is essentially our intuition. It's the fast, intuitive, but kind of approximate, sort of, we apply simple heuristics often, and hard to explain kind of decision-making, right? This is the kind of decision-making we use all the time. 99% of the time, this is what we're doing, is it's just sort of the correlative, quick, we're driving a car. Once we learn to drive the car, at least we're using all system one. We're not thinking very hard about it. In fact, we probably can't even remember where we were sometimes because we were thinking about other things at the time. When we're talking with friends or even business colleagues, most of the time it's just system one. Using it all the time, it's easy to use. The other mode is what Kahneman calls system two. And this is the more logical, step-by-step, methodical, precise kind of thinking, but it's a lot slower. And the other big difference between the two is system one, it's intuitive. It's hard to explain, right, how you made the decision, right? There's a lot of emotion and feeling involved often in system one. And so it's sort of inscrutable, hard to explain. System two, because it's step by step, it's logical, it can be explained to anyone. You could write it down and so forth. Now, evolution is an optimizer, and nature has found this combination is optimal. You've got to have both. Because, for example, if the lions are chasing you, you better be using system one, right? You don't have time to sit down and go through lots of methodical sort of thinking. You better react. On the other hand, if you've got a complex situation with relationships with other people or thinking through constructing something, you've got to go step by step, logical, and particularly if you want to explain it to somebody else, how to do something, right? And so system one is also indispensable, at least for humans, and most animals are primarily almost all system one driven, as far as we can tell. It's humans that have more and more of the system two layered on because of our complex relationships and societies and so forth. And again, the key is you've got to have both. If both weren't important, we wouldn't have them, because system two is, quite expensive from the standpoint of, takes a lot of brain power, and we don't like to do too much of system two. Yeah, we're taking a math test, we've got to do it, etc. System one's just easier, but you've got to be able to apply both. Okay, so that's humans, and system one should sound quite familiar to this audience, right? Because it's essentially tacit knowledge. It's essentially what generates tacit knowledge is sort of system one capability. It's intuition. It's I've got a hunch, but hard to explain to anybody, exactly why, I think this is better than that. And I represent it here with sort of a network diagram, right? Nodes and connections between the nodes that sort of dynamically change over time. Something's going on there. It's learning. That's what the change part is. But exactly how it's making the decision, not very clear, right? And if we look inside the brain, in the head, it's basically just this kind of thing going on. And how's it doing its magic? Not clear. Now, system two should also sound familiar. I mean, it's explicit knowledge, right? It is basically the stuff that is methodical, step by step, that we can write down and explain to other people. And I represent that as sort of a tree, because a lot of explicit knowledge boils down to sort of step-by-step processes. If I do this, then something happens, and then there's a next step, and I keep treeing out the options as far as I can go, and I kind of work backwards off into, okay, this is the kind of decision that's best given the circumstances. So again, tree and sort of tree search is often kind of a good representation of what we're talking about with system two, and also explicit kind of knowledge that we can put in different forms, diagrams, writing, and so forth. Okay, so again, this is humans. We've got these two cognitive modes. Nature has found they're optimal to have both. This is an important point, even, just to linger for a moment. Back in my era in particular, I think things have changed, of knowledge management. Tacit knowledge was looked down upon, right? We really want to get everything into explicit knowledge. But when you think about it again from the way nature is optimized, it's clear tacit knowledge is indispensable. It's the only way you can deal with highly complex situations where there's a lot of data changing and changing rapidly. Just the explicit knowledge doesn't work. It's not sufficient. And that's why we have system one / tacit knowledge. And we should embrace that reality that both are important. And what we're discovering is the same thing in our computer systems. Because computing, if you think about it, has been historically entirely system two or explicit kind of systems, right? And that's because we tell the computer exactly what to do. If this condition, then do that, and so forth. Big chains of this, which we call programming the computer, or we put content in there, basically. Again, explicit because we can write it down. And this is the way computing has been for the 6 or 7 decades since its inception. We don't even, it's the way we think computers are. Computers are just sort of, this logical system. It's just the way it is. It's the way it is because we have taken our system two and put it into the computer. And that has changed very recently with the advent of artificial neural networks, which in practice we often call deep learning, because deep learning just means there's multiple layers in the neural networks, sometimes many, many layers, these big systems these days. And it ultimately delivers a system one type tacit functionality. And it's taken us some getting used to there, because again, our whole experience with computers has been purely system two, and we never even thought we were missing anything necessarily with sort of a system one, a tacit sort of capability. But now we're realizing you really need both for intelligent systems. For systems to be truly intelligent in a variety of types of environments, particularly complex ones, you've got to have both. Both are needed, just like in humans. We're kind of just recapitulating or relearning what nature has already discovered. And I'll give you a couple examples of that, starting with games. And particularly, let's start with the game of chess, because chess was one of the first games that computer scientists attempted to try to program and ultimately make better than human players, right? So it goes way back to the 60s and 70s. And the way we built those systems was using explicit knowledge, right? We first of all loaded in all the first 10 moves or 15 moves of chess openings, which humans had discovered were kind of optimal. And we loaded those in to the computer. So it was like a pure memorization. It didn't have to do any thinking, those first 10 moves or so typically. And then we basically put in something like a tree search algorithm, which basically just says, the computer predicts essentially what the opponent's going to do. Then given that opponent does that best move, then the computer thinks about what their reaction would be and chains ahead as far as it can, maybe 5, 6, 7 levels of thinking that way. Can't go to the end of the game because there's too many positions and options in chess. It's like greater than the number of atoms in the universe. So even with quantum computing, we're not going to solve chess. But by having levels in computational power that could go a little further than even the best human, by 1997, this programmed explicit approach could beat the best human, Garry Kasparov. And that was continued to be the state of the art. There was incremental advances made, and because of the additional computational power, Moore's law, they got better and better and better. But then suddenly, a few years ago, Google introduced neural networks into the equation here, right? This was a tacit kind of capability that was sort of pattern matching, and it basically self-learned by playing itself to detect positions or patterns that would lead to winning results. It just played thousands and thousands of times. And by doing that, it actually recreated the optimal openings that humans had discovered over a century or so of play. So it did that, but it could go further and further after the openings. It understood positions that patterns that also would potentially lead to better winning situations as well. Now, if you ask the system how it was understanding and explain itself, it couldn't, right? It's pure neural networks. But at some point, that pattern matching by itself is insufficient too. And so at some point, you still apply the tree search. But the difference is the pattern matching, the intuition narrows down that which you're going to really apply sort of this tree logical explicit method. So you can go deeper, narrow things down than the traditional method. And that system beat the best program system. Combination was best. And that has been found to be true for other games like Go. Many of you would be familiar with that game. Beat the best human as well. That's even more computationally difficult than chess. Other games that are hard because there's hidden information like poker and also bluffing, this combination is winning there. Almost all games have succumbed to this combination. And in that sense, they're more like humans because they've got both intuition and explicit logic as well. It's just that with enough computational power, they can go even further than humans with this combination. Now, besides games, they're also doing very valuable things like protein folding is extremely computationally difficult to do. It's basically strings of amino acids in a linear form, and they fold up in all sorts of different complex positions. Huge number of possibilities. And it's taken typically, human scientists years to figure out one protein folding. So the way one protein folds up. And it's important to understand those because we want to know how they fold, because proteins have key effects in the body. Well, this kind of combined intuitive tree search capability has been applied to that problem, something called AlphaFold, that essentially solved much of the protein folding problem. So we know how proteins fold, which has potentially a dramatic effect in the healthcare and life sciences area. Another area that's going to be very familiar to you is the generative AI, particularly the large language model kind of AI that we can converse with, represented by, for example, ChatGPT. That's an interesting history where, years ago, we used to try to do that with explicit programming. Another thing where we would try to put in explicit rules for grammar, and then if somebody asks this question, this is how we respond, and a lot of if-then explicit sort of stuff. Problem with that is it didn't scale, right? It just it basically has limits. You can do certain little things with call centers and so forth, but if you want to have a fluid conversation, it just does not work. And so a few years ago, starting in 2018, we started applying deep learning neural networks to the problem, and self-learning, here learning from maybe much of the internet, resulting in something we call large language models. And these kind of models are, again, more intuitive and frankly, more the way a child learns language. I mean, by and large, a child doesn't learn language by we tell them all the grammatical rules and they have to memorize the grammar, et cetera. I mean, we do some of that in school, but mostly they just pick it up. And even without school, they're going to pick it all up, right? It's intuitive. And so we've rediscovered what nature, again, has already built into us. Now, that's all great stuff. And those of you who've used this kind of capability, it's remarkable. It can carry on a nice conversation very fluid. The grammar is almost always right. That alone is somewhat surprising for those of us that were dealing with more explicitly programmed things a number of years ago. But they're a little bit superficial, right? When you dig down, you find out, well, the logic isn't really there, right? They're just kind of correlative again. They're probabilistic. Again, they're intuitive, but sometimes wrong. They get facts wrong, right? And so a lot of the research right now is how do we, again, get the best of both worlds? How do we get the fluid, the intuitive sort of language capability, but coupled with the stuff that we have come to expect from computing over the years, which is facts, right? Which is logic, which is, we ask how it arrives at some conclusion. Why? We want to ask why, and we want answers. And to do that, we've got to have more of the explicit sort of knowledge built in, sort of more like, again, tree sort of things. Here's the logic, etc., coupled on. And you see that with now search engines that have the conversational interface, but now they can go out and check the facts before they bring stuff back to you, just to make sure they're factual. That's a simple example of putting these two capabilities together. More complex ones are where we actually put in more logic modules to make sure the sort of intuitive thinking, the first cut stuff, actually makes logical sense. So we're, again, rediscovering what nature already discovered, is that for many kinds of applications, we want both tacit knowledge and explicit knowledge. We have to have tacit sort of based learning and explicit kind of capabilities to be best, to be optimal for most things that we work with in our lives and that we use computers for. Okay, so now let's come back, though, to value, because, again, wonderful technology, but we want to keep our eye on value. And that means we need to come back to our decisions in DLA diagram. And to drive value, again, we need to make DLA processes more effective. So how do we do that? Well, like any sort of flow or process, we have to find the limited constraint that's keeping us from getting more value, from making more effective decisions. There's always going to be a limiting constraint or bottleneck in a DLA process. And finding it, our system one intuitive capability can lead us astray often. We're not that good in complex situations of knowing where limiting constraints are. So we actually have to apply more system two kind of thinking, logical, methodical thinking. And that really means starting with the decision and working backwards and being very careful to examine each of these elements and determine where the limiting constraint is and be very sure of that. I have a lot of detail on how to do that in my book, and I don't have time to go through it in detail here. But again, I would just say it's good to be methodical to find the limiting constraint. The beauty is, once we find the limiting constraint, because we now have this combination of explicit and tacit knowledge in both humans and machines, we've got an opportunity to resolve those constraints in ways that we never could before, and therefore unlock value in ways that we never could before for our organizations, right? And a couple quick examples I'll give of that that's already occurring is in things like supply chain, right? Supply chains for large organizations are very complex. Lots of steps, lots of data, lots of uncertainty, lots of just moving parts, right? Happening often fairly rapidly. Whenever you see a situation like that, it's kind of a sure bet that explicit programming modeling is going to struggle a little bit, right? It's going to give you probably, something relatively close to optimal, maybe, but it struggles with highly complex kind of situations. That's where deep learning neural networks tend to be best, right? They can detect these they can learn to detect these patterns and learn to sort of optimally respond to them, or at least be good enough to then pass on to the more explicit algorithms that you generally still need to basically fine tune what the pattern is suggesting. So in supply chain, inventory management, and so forth, we're seeing more and more combination again, deep learning plus the explicit algorithms, logical algorithms. And of course, humans still have a big advantage in that we can see across things and have a greater scope of understanding than any of the systems, even in combination. Because, if you think about it, if I've got a large language model, I mean, it can do some terrific things, but if I try to plug it into a supply chain and have it do something or play chess, it's worthless. It can't do anything, right? It's wonderful, but it's still quite brittle, unlike us, where it's quite flexible. So from the standpoint of oversight and scope of understanding, this is where the combination of humans and machines, both tacit and explicit, come to the fore. Another area that's the combination is making big inroads is like consumer behaviors, consumer sentiment, and understanding how to market and so forth based on that. It's another area where just a lot of moving parts, lots of data, lots of things, complex, and you ought to be thinking, gee, something like intuition, deep learning might be a player there, and indeed it is. Like in recommender engines, one of my fields, now all the most sophisticated recommender engines have basically a deep learning part, but they often still have some explicit algorithms as well. So they've got kind of both. See it more and more in most applications, anything with sufficient complexity, things that we expect require intelligence, we're going to see combination of tacit and explicit kind of capabilities in our machines, and humans applying their tacit and explicit capabilities as well, and basically improving DLA processes. And this is where I think knowledge managers and learning and development people have a huge role to play, because you can see from this webinar that what I'm saying is a lot of stuff that we talk about is like technology and stuff really is coming back to the way humans interact, including tacit knowledge, which is very new. And you have the kind of understanding that can help harness that kind of capability from based on your experience in ways that others won't. So I think it's a big opportunity for this community. And I'm going to stop here and we'll take some questions and comments. And I thank you for your time.
Thank you, Steve. Thank you very much for your wonderful presentation. Highly informative, inspiring, and valuable. And now we have about 10 minutes, and let's move on to the Q&A. Yeah, we have collected some questions from the audience during the live streaming, and I'll put several of them in the chat. And some of them are in Chinese, and we have translated them into English.
Okay, I don't see them in chat.
Yeah. Yeah, here. Okay.
You may have to read them.
那我们刚刚呢，就非常感谢我们 Steven 先生的精彩演讲。那现在进入我们的问答环节。那大家如果有问题的话，可以随时打在公屏上，然后我们的工作人员会反馈给我们的嘉宾，我们会进行在线的实时问答。
Okay,
好，第一个问题是，那么在决策过程当中，隐性知识和显性知识的区别是什么？他们扮演什么角色？ The first question, what distinguishes tacit knowledge from explicit knowledge in decision making, and what roles do they play? Steve, please.
Yeah, so that's the fundamental question right there is, and it applies both to humans and machines. So tacit knowledge is basically the kinds of, and we can call it tacit learning, okay? Tacit learning creates tacit knowledge, is the kind of learning that you do when you simply can't compute something, right? It's like this big buzzing confusion, complex environment, which is most of what we deal with humans, right? We have, like I said, all this data coming in every second from our sensory organs. There's no way you could ever go through sort of a tree of, should I do this or that or the other thing? It doesn't make any sense. So tacit learning and knowledge is what you do to filter the world into then deciding. Sometimes you just decide using tacit knowledge, period. And for humans, that's most of the time. Most of the time, that's what we're doing. We just learn patterns and we're without thinking too much, just like I'm doing now, right? I'm not thinking that much. I've learned this stuff over many years. I'm just, boom, it's coming out. And it's quick. That's what we do all the time. And it's indispensable. You've got to have it. But sometimes, and psychology has shown this, sometimes in complex sort of situations, you need to have the explicit knowledge, the explicit learning, the logical, causal, right? A lot of tacit knowledge is a bunch of correlations, right? Okay, this is close to that, so forth. And I just sort of, boom, shoot it out there. Sort of approximate. But sometimes we got to be very careful and precise. And that's where the explicit part comes in. And the other part that explicit comes in, if we've got to communicate something to someone else, it's got to be fairly explicit. It's very difficult to do that with tacit knowledge. So that's for humans, and machines are the same way. Just as I said, with machines, we've been missing all these years the tacit knowledge. We've just had this explicit stuff, and it could do a lot of things, but it couldn't do like language, right? It wasn't until we started putting, sort of large language models and neural networks together that you can do that kind of stuff. So we're just finding out with computers what we've been missing all these years because we didn't have sort of the tacit part there. So for most things, you're going to be using tacit knowledge for almost every decision. And it's just a question of then are you going to layer on explicit? And that's why if you're a knowledge manager and you're mostly just focused on explicit knowledge, you're missing. I know there's other presentations of iceberg showing here's all the tacit knowledge under there. That's exactly right. It's mostly tacit, and we mostly have never captured that in our computer systems.
Thank you. 那针对第一个问题，就是决策过程当中，我们隐性知识和显性知识的区别是什么？他们又扮演什么角色？那首先，这个隐性知识它主要是源自于我们的隐性的学习，正是因为隐性的学习，然后导致我们能产生一个隐性的知识。那这个隐性知识它并不是通过我们的像计算机一样通过一些计算能力得出来的，它其实是比较复杂的。因为就像我们的大脑，我们的大脑每一秒都在接受着各种各样的数据，我们不可能像计算机一样再去进行各种各样的处理。那我们呢，主要进行的，首先，当我们接受数据的时候，我们首先进行一个过滤，这是我们就是人一个可以主动的行为，我们可以去思考，就是用比如说通过怎么样的模型来处理这样的数据。那这个过程呢，其实是非常快的，这个隐性学习过程是非常快且非常迅速，但也同时是必不可少的。那在遇到非常复杂的这种情况决策的时候呢，那我们的这个显性知识它又起到了很重要的作用，因为显性知识它是更有条理、更有逻辑的，因为它涉及到很多的，比如说因果关系。而且它的产生的这个知识呢，也将产生的这个决策也会更加的准确一些。那特别是我们在日常沟通当中啊，如果是你用隐性知识的话，其实是很难的，更多的是我们的显性知识在发挥作用。那对于这个机器，我们 就像我们近几年在各种就是人工智能比较发达的时候呢，我们更多的是把利用就是让它具备一个显性知识，更多的植入显性的知识，让它去处理，比如说一些我们的大语言模型啊、神经网络的这些诞生，然后都帮助了我们机器，然后能够迅速高效的去处理我们的这些显性知识。那总的来说呢，就是我们在决策过程当中，那当然首先呢，就是能够我们因为很多东西它都是直觉的，它非常是迅速的，它可能不那么准确。我们首先会运用到我们的隐性知识，然后我们呢会再带入我们的显性知识，让我们的这个知识这个决策就是更有条理、更精确。Thank you for your answer. And let's move to the second question. Second question, this question might be similar to the first one. 那第二个问题可能跟第一个有点像，就是隐性知识如何助力决策过程，就是 How does tacit knowledge contribute to the decision-making process in humans?
Yeah, well, it relates to what I just said. I mean, almost everything we do as humans, almost every decision has some element of tacit knowledge attached to it. The exceptions would be very narrow things like, if I'm taking a math test or something, maybe it's almost all explicit, but even there, we're going to be doing just like people would do with chess or Go. We're going to narrow down things using our tacit knowledge first. We're going to have a hunch, and then we're going to kick in our system 2 or explicit to kind of try to calculate things and double check our tacit knowledge. So tacit is a first cut. It gives us a quick answer or set of options. Then we apply explicit to be more precise. That's almost always the case in everything we do as humans. Again, now with machine learning, artificial intelligence sort of stalled out in the 80s and 90s. It didn't really do much. It's only been since 2012, 2013, when we started putting tacit knowledge into computing, that it's gotten very interesting and can do useful things. And it works the same way as humans. It basically detects patterns, narrows things down, and then maybe we layer on top of it explicit learning.
Thank you. 那第二个就我们隐性知识如何助力决策过程。那其实隐性知识它发挥的作用呢，就是不只局限于这个我们的决策过程，其实是渗透在我们每个人我们做的每一件事情上。就像我们的这个人，就是我们的做的决策，那它都要就是隐性知识都发挥了非常关键的作用。那它首先就是我们在比如说不管是可能我们做，比如说我们进行一个数学的测验，那这个可能主要是显性的知识在发挥作用。但比如说我们进行一些稍微复杂一点的，像我们刚刚举到的例子，像象棋、像国际象棋、围棋，做这些事情的时候呢，隐性知识它首先会帮我们迅速的去缩小一个范围，因为它的反应是迅速的，我们会在大脑里产生一个非常迅速的一个答案，然后就是迅速的缩小这个范围，然后在缩小范围以后，就是我们的就是第二个系统了，就是显性知识开始发挥作用了，就像机器也是的，它开始用第二个系统，就是运用它的计算能力，帮助我们去计算的出更精确的答案。所以就不管是人还是机器，其实都是第一步，我们的隐性知识迅速帮我们去缩小范围，然后再通过我们的显性知识帮我们更精准的去得到这个答案。Thank you for your answer. And the third question. 好，我们现在来看第三个问题啊。第三个问题就是组织可以用什么样的方式去，比如说衡量这个隐性知识纳入 AI 这些计划的这个投资回报。The third question is, in what ways can organization measure the ROI of incorporating tacit knowledge into their AI initiatives?
Okay, well, that's a very good question, and it's a more difficult question, but not that difficult because it's sort of narrowed to AI. If we broadened it in general,
Yeah,
it
yeah.
would be tougher. But for AI, like anything else, the best thing to try to do is simply measure the current state of the system, and then experiment with adding, let's say, a capability for more like tacit capability, maybe neural network, deep learning kind of capability, and get a sense of how much more effective the decisions would be with that technology. This is the key thing with technology, is never let the technology drive things. It's always a question of how much more effective is the decision going to be. If the decision is any more effective, or at least you're lowering the cost, given you're making the same decision, then the technology is not valuable and there is no ROI. So you have to measure it from the effectiveness of decision. And that's key because most companies, most organizations do not do that. They're just looking at productivity. So good question.
第三个就是组织用，比如说什么样的方式去衡量这个隐性知识在 AI 计划中的获得的投资回报。那这个问题回答呢，就是我们更多应该是衡量，比如说看一下这个系统，比如说这个 AI 它目前当前的状态，因为我们的这个隐性能力啊，它比如说现在我们主要通过机器主要通过这个计算机，它通过一些技术，那这些技术比如包括深度学习，包括神经网络，那这些技术呢，它可能是比如说可能帮助我们，然后能够更有效的去将这个隐性知识就是进行一个更有效的利用。但是这个衡量的话，其实这个问题其实更其实精准一点的。因为机器它不可能说我们不可能拿机器去衡量它这个有效性。那我们肯定更多的是通过我们的人，那就是主要的。其实这个问题归结到底的根本问题是，就是如何去让我们如何能够更有效的去做出决策。因为这个主要的衡量标准就是就是我们就是作为组织里的人，我们在做决策的时候是否更加有效，然后从这个角度去看，就是隐性知识它就是纳入 AI 计划，然后给我们带来的这个投资回报。那这个问题呢，相对前面那个要是难一点，因为我们这个问题呢，它不可能说从机器的角度去衡量，这是不现实的。我们更多的是从我们人做决策的有效性方面，然后来就是可以看出这个隐性知识纳入 AI 计划它的这个成果。Okay, another question. Okay, this is asked by the same person and also. 那第4个问题是说，在试图利用 AI 系统中的隐性知识时，组织会面临哪些挑战？然后他们会又如何克服这些挑战 ？Okay, the fourth question is, what challenges do organizations face when trying to leverage tacit knowledge in AI systems, and how can they overcome these challenges? Yeah, please.
I mean, a key challenge, to be honest, is the technology is moving so quickly that you've got to be careful of doing things that are obsolete in literally months at this point. So one thing is just be careful. And my general advice for organizations is don't lock into big, expensive things too much. Try to ride the technology waves. Most of what you're going to use is going to be built by external companies, right? You're not going to want to generally build too much of the real detailed technology yourself. You're going to basically let it operate on your data to create the tacit knowledge, but you're not going to actually create the models. So that would be number one. The other thing, though, I would say is, again, going back this question, going back to some of the other questions, you've always, this is an exciting time where the technology is so wonderful that we can get carried away. It's my field, so I get very excited about AI, but we've always got to go back to the decision and that data to learning to action process that supports the decision, and understand where the true bottleneck is. Because sometimes the true bottleneck or constraint is not going to be the tacit learning, it's going to be the data, right? And if you don't have the data, the learning isn't going to work. Or it could be a people issue, right? I mean, where you've got all the wonderful data information coming out of the model, but the people don't believe it. So you've got a trust problem. So you've got to understand the DLA process, the data learning action process, to ensure that you're going to get value from your tacit knowledge, whether it's AI or humans.
Yeah, thank you. 那这个问题的回答呢，就是我们在比如说是应用 AI 系统中隐性知识会面临哪些挑战？那这个挑战呢，其实最根本的就是技术，因为它的技术发展实在是太快了，因为你随时可能就是要防备这个技术可能它很快就过时了。那针对这个呢，我主要有2点建议。首先就是大家不要就是在这个比如说一些技术上花过多的成本。你们可以比如说在运用哪些模型技术的时候，我们可以比如说可以外包，我们可以通过第三方来就是获取这些技术的资源。因为如果你自己去比如说开发一些模型啊软件呢，你可能会要花很多细节在上面，然后可能会就是花大量的成本，然后可能过一段时间它又很快就过时了。那第二点呢，就是说我们要回归到这个本身，因为这个不管你在做这些什么事情的时候，你回归的都是回归到我们要做的决策上面。那这个决策呢，就是要回到我刚才提到的这个 DLA 这个过程，就是数据学习行动这样一个基本的过程。因为这个过程呢，它是更能够就是驱动我们去做出决策，给我们组织带来真正的价值。因为有时候这个里面呢，也可能不只是数据的问题，也有可能是一些人的问题。那不管怎样，就要回到这个根本上的，比如说数据学习行动这样的一个过程。基于这个过程来去思考，然后进行这个流程的推进。Thank you, and let's see. Maybe we have the final question, and the time is very limited. And this is the new one. 最后一个问题啊，这个问题是最近我们 AI 技术因为的进步是如何能够促进这个隐性知识和计算机系统的整合。The final question is how do recent AI advances facilitate the integration of technology into computer systems?
Yeah, well, that's really the only way to do that that we know of is through these neural network deep learning. That's really the only way you're going to learn tacitly. Now, some tacit knowledge we can kind of extract into explicit knowledge and put it into the machine, the way we've done that for many decades. But if we want to learn tacitly, have the machine learn, we're going to use neural networks. There is no other way to do that we're aware of. And that works whether it's image data. We've been doing that for years. We can tell a dog from a cat in an image and so forth. If we ask the computer, how does it know? There's no way it could articulate that. It's clearly tacit knowledge. Now, though, it's working with these large language models in language. It'll be generating videos, et cetera, et cetera. So really, neural networks, deep learning is the key. And there's really no other right now technology that's a rival for that capability.
针对最后一个，就是我们 AI 的进步是如何促进隐性知识和计算机系统的整合。那这个呢，主要是 还是就是仍然是通过2种方式，第一个是神经网络，第二个是深度学习。那只有通过这2种方式，那机器它才能够去做一些隐性的学习。那我们其实现在我们常用的一些方法，就是我们可以将隐性知识能够让它就是说显性化变成显性的知识，然后再去输入到机器当中。但是如果要让机器自己去，比如说能够去具备隐性的能力去学习的话，那只有通过神经网络。像我们现在 AI 的技术，它可以比如说通过各种图像啊，可能通过文字生成图像，生成视频，比如说通过大语言模型，它就能够生成一个视频。但像机器，它具备这种能力，比如说，但是如果你问机器你是怎么做到的话，它又不能准确的表述，因为这是属于它隐性知识的范围。那是综上，主要的我们让隐性知识和计算机系统整合，还是通过这个神经网络和深度学习这2种方式。Thank you, Steven. Thank you very much for your fantastic presentation, and thank you for your support for GO-TKM. And it's been a great honor to be with you. Thank you very much.
Thank
And
you.
we hope that we can continue to collaborate in the future.
No, that'd be terrific. It's delighted to do it. And, as you can tell, I think tacit knowledge has been undervalued, and AI is proving its value if anybody ever doubted it. So I think GO-TKM is a wonderful organization and direction. Happy to do it.
Oh, thank you very much. And good to see you, and have a good night.
Bye-bye, everyone.
Bye-bye. Thank you. 好，以上就是我们今天的讲座 Steven 先生的分享。那他如果想就是需要获得本场演讲的回放的话，可以联系我们的工作人员。如果想获取本场讲座的资料，比如刚才的 PPT，当然也可以扫这个下方的2维码，然后联系我们的工作人员领取。好，在这里我们也进行一下下期讲座直播的预告，是在3月6号。这个是由我们的 Adam 博士，他来自挪威，是隐性知识管理方面的资深顾问和思想领袖。他给我们带来的话题是过度自信或许是成功的关键。那这个过度自信主要源于邓宁克鲁格伯这个理论。那他在这里呢，他就是提出了一个悖论，我们过度自信也许能够帮助我们获得成功。好，对这场讲座感兴趣的朋友可以扫下方的2维码，然后报名参加我们的这次讲座。好，最后我们在这里预告一下，我们就是 Mentoring 蒙科以及组织隐性知识管理全球智库 GO-TKM， 我们即将在今年的10月份，10月21号、22号在瑞士达沃斯举办隐性知识管理达沃斯论坛。这个论坛呢，我们是线上线下同步进行的。那大家对论坛如果感兴趣的话，可以就是点击下方的这个网址，是 GO-TKM.org。这里面我们的官网有更多的这个会议详情、论坛详情以及门票信息。那同时我们也提供了大量的报名优惠。那如果你报名越早的话，自然是优惠更多。我们可以扫这个下方的2维码，联系我们的工作人员去获取我们的报名优惠。我们也非常期待大家加入我们，让我们一起助力这个隐性知识管理的发展。好，以上就是本场的讲座。好，我们下期再见，谢谢大家。 伟东，等一下，我看一下哦。嗯。